So mass spectrometry is a way to measure, that's what the metry is referring to. For example, the metric system is a system of measurement, so this metry is a way to measure the mass of a compound. And what you're going to do is you're going to get a bunch of different masses that will spread out in a spectrum when you do this, use this technique of mass spectrometry. So the way it works is you'll have a small molecule, let's say methane, so just one carbon and 4 hydrogens. And you have to vaporize it, so it has to be a gas. And then you pass it through a chamber. Now, you, of course, wouldn't do this with just one molecule. Even with the smallest puff of gas, you have hundreds of trillions of molecules. So you'd send a bunch of these gas molecules through a chamber, and when it finally gets out of the chamber, you hit it. You bombard it with a stream of high-energy electrons traveling fast. So they're traveling down, shooting out. Usually how those are made, although they can be made in several ways, but one of the ways that those are made is you can take a metal and just heat it up. And the electrons in a metal aren't stuck around individual atoms. They travel over all the nuclei in the entire metal. And so as you heat a metal up, they move faster and faster, and the nuclei vibrate faster and faster, and eventually they knock out these electrons. So you've got this stream of electrons, the molecule passes through it, and as it passes through it, it gets hit. Now, one molecule will get hit and just break apart in one way. But since even in the smallest sample of gas that you pass through here, there are hundreds of trillions of molecules, every possible way that this molecule could break apart will break apart. It'll happen. And so you could imagine that only this first bond breaks apart. And so what you get on the other side would be something like this, and this would have a positive charge on it. We'll talk about this. So this is an example of one of the types of things you can get. We'll talk about what happens to the other things in a second. A molecule could be pretty unlucky and 2 bonds would break. And in that case, 2 hydrogens would fly off, and you'd be left with a positive charge. That's another possible way that this could fragment. Another molecule of the trillions that pass through could be really unlucky. 3 bonds break, and so you're just left with 3 hydrogens popping off, and it would have a positive charge. Or you could imagine the most unlucky of all 4 bonds get hit by these electrons as it passes through the beam, and you're just left with a carbon atom that has a positive charge on it. So now you have all these species, all these molecular guts traveling in a stream. In addition to all of those, you have other ways that this could have fragmented. It could have fragmented and the electrons could have stuck on the fragment, so it has a negative charge instead of a positive charge. It could even have fragmented in a way, it could have broken apart in a way that left no charge on the molecule. Maybe the charges even out. So you get all of this stuff and a whole bunch of stuff that I didn't draw. And the reason why I didn't draw it is because you take all of this stuff, you take all of these molecules and you pass them over a magnet. You pass them in between a couple magnets. So you'd have magnets here and magnets here. Now, anytime a charge moves, it creates magnetism. So moving charges respond to magnets because they have magnetism associated with them. Now, so when these pass through the magnets, they'll turn. Instead of just going straight and keep traveling, they'll turn because of the pull of the magnets. And so what you can do is you can position these magnets in such a way that you have a detector over here. And when these charged particles, when these charged particles go through they turn because of the magnet and they hit the detector. Now, I should have it this way, sorry. So they turn and they hit the detector because of the pull of the magnets. If anything that has a zero charge on it, so we said these are just some examples of what could come out when you pass molecules through this stream of electrons. Anything with no charge on it just goes through and hits a wall. It doesn't hit the detector. Anything with a negative charge would go through and then curve the other way. The magnets would interact the opposite way with it. But everything with a positive charge will go through, turn because of the magnets, and hit the detector. The fragments that are the lightest, that are the least massive, those turn the most. And the fragments that are the most massive, those turn the least. Imagine you're driving a small, tiny car. It's easy to turn the car left and right. Imagine you're driving a really big, heavy truck. It's hard to turn the truck left and right. The more massive something is, the harder it is to turn it. And so when these go through the magnets, the heavy things don't turn that much, and the light things turn a lot. And so based on how much they turn, they'll hit a unique place in the detector. And based on where something hits the detector, you could tell how massive that fragment was. And so you end up with a spectrum. A spectrum of these different masses. One other note, you might say, well, what about things that have like +2 charge or +3 charge? Do those fragments exist? And they do, but the bigger the charge, the less stable the molecule, and usually those molecules won't survive to hit the detector. So for our purposes, each of these fragments will all have a +1 charge. The zero charges went straight through, the negative charges went the other way, only the positive charges went toward the detector, and only the +1 charges survived long enough to make it there. So the charge we'll always have will be +1. Okay, so we were just saying, based on how the heavier molecules won't turn as much, lighter molecules will turn a lot. And so based on where a fragment hits the detector, you can tell how massive the fragment was, because it'll either have to turn more or less to hit a detector in a certain place. And so you'll get a spectrum. On the x-axis of the spectrum, it's basically going to be the mass. Now, technically, it's not the mass. You won't see the word mass there, but you'll see what's called the m/z ratio, the mass to charge ratio. That's the mass divided by the charge. The z stands for charge. But since the charge, as we've seen, is going to always be 1, +1, the mass to charge ratio is really just the mass. Anything divided by 1 is itself. So you have this x-axis that's going to be the mass. And when these fragments hit it, when these fragments hit it, they become peaks with certain masses. So for example, you'd have a mass of 12 here, and so you'd have a peak that represents this carbon atom that has a mass of 12. Remember, the masses are the numbers at the bottom of the box on the periodic table. If you look at the box for carbon, there's a 12 underneath there. That would be the 12 that corresponds there. And there, at 13, there will be another peak, and that would represent this fragment hitting the thing. And at 14, another peak, and that would represent this fragment. And at 15, there would be another peak, and that would represent this fragment. Now the y-axis here is the percent relative abundance. The percent relative abundance. How much of this fragment hit the detector? If a molecule is the way I've drawn it here, if a spectrum is the way that I've drawn it here, then this fragment would have hit the detector most often because it's the highest peak. This fragment would have hit the detector least often because it's the lowest peak. All right, let's go back to our example of the methane molecule traveling through this stream of electrons. So when this travels through this stream of electrons, something very special can happen when this travels through. Instead of an atom getting kicked off, one of these electrons might hit the bond. And when it does that, one of the electrons in the bond gets knocked out of the molecule. And so what you end up creating on the other side is the same molecule, but instead of 2 electrons in one of the bonds, you just have 1. Now that is not a very stable molecule, so it's not going to survive for very long. But the unique thing about it, so first of all, it lost 1 electron, so it'll have a positive charge. Remember, an ion is something that has a charge. You can have a positive or negative charge. If you have a positive charge, you're a cation. The T sort of looks like the plus sign. A cation. And if you have an unpaired electron anywhere in a molecule, the molecule is called a radical. That means you have an unpaired electron. And so this here is a radical cation. Radical because of the unpaired electron, cation because of the positive charge. Radical cation. And the unique thing about that radical cation is that it basically has the same molecular mass as the original molecule. So that'll go through, that'll create another peak. You would have that radical cation and that would have the same mass of the molecule. That here would be 16. Oops. 16. Sometimes it's the highest peak, sometimes it's not. I mean, none of these are really stable, but this also is very often not stable. But in the case of methane, it happens to be the highest peak. Just for the sake of illustration, I'm going to say this other peak is the highest peak, although in the true spectrum of methane, that radical cation is the highest peak. Because this radical cation has the same mass as the original molecule, that peak is really important. That peak lets you determine whether you have a certain molecule or not. If you have a certain molecule, you'll have that peak at the far right that has a mass that you know that molecule has. And so it has a special name. It's called the molecular ion peak. And the symbol for that is capital M. That's representing the fact that it has the same mass as the original molecule. A plus sign, because it's a cation, and a dot. And the dot is symbolizing the fact that it is a radical. It has that unpaired electron there. So that is the molecular ion peak. Really crucial peak. You can, if molecules with different molecular masses will have a different molecular ion peak. And so that is how you can solve this specific problem. The problem is asking you, how could you use mass spectrometry to distinguish between these compounds? Well, notice, this compound has 1, 2, 3, 4 carbons. So we have carbon here, we have oxygen, and we have hydrogen. We have 4 carbons. Each carbon has a mass of 12, so that's 48 coming from the carbons. For oxygen, we just have the 1. Oxygen weighs 16. Look at the box in the periodic table. Underneath the O, the number, that's where I'm getting these masses from. So that's 16 atomic mass units coming from oxygen. And hydrogen, we have 1, 2, 3, 4. Each of those carbons has just 1 hydrogen on it. So we have 4 hydrogens. Each hydrogen has a mass of 1, AMU, and so that's 4. So that would be a total mass of 68. And so on the mass spectrum for this molecule on the left, you have the M to Z ratio, M to Z ratio, and the percent relative abundance. And what you would notice is that you would have a peak at 68. That would be your molecular ion peak for this molecule. Compare that. Compare that with this other molecule. Here we have 1, 2, 3, 4, 5 carbons. So we have carbon in this molecule and hydrogen, that's it. We have 5 carbons, each carbon weighs 12, so that's 50 plus 10 is 60. And then for hydrogens, we have 2 at the top, 1, 1, 1, and 1. So that's 1, 2, 3, 4, 5, 6 hydrogens, and each weighs 1, so that's 66. So on the mass spectrum for this molecule, you have that M to Z, mass to charge ratio, in other words, which is basically the mass on the x-axis, the percent relative abundance, how many of the molecules you have on the y-axis, and you would notice that you'd have that molecular ion peak at 66. Oops, I should have said, this is just 6 coming from the hydrogens, add that together, 66. So because these molecules have different molecular masses, they will have different molecular ion peaks. And so you can distinguish between them by taking their mass spectra and seeing which one has a molecular ion peak that corresponds to one of these molar masses. You could do the same thing with B. So we'll just see the different molecular masses. In this one on the left, benzene, we've got carbon and hydrogen, that's it. We have 6 carbons. Each carbon weighs around 12, so that's 60 plus 12, so that's 72. We have 6 hydrogens. If you notice, there's 1 on each of the carbons. All the carbons have a 0 formal charge, so they all need 4 bonds. Each only has 3 bonds drawn in, so there's an invisible bond to hydrogen. Hydrogen weighs 1, so that's 6, so the total mass should be 78. And if you look at the mass spectrum, you would have an M to Z ratio, mass to charge ratio, which is really just the mass. On the x-axis, percent relative abundance. On the y-axis, how many of the peaks hit here. And you would notice that at 78, you would have this molecular ion peak. Whereas, if you had the other molecule, this one, you notice here you have carbon, nitrogen, and hydrogen. We have 5 carbons, each carbon weighs 12 AMU, so that's 60. We have 1 nitrogen, each nitrogen weighs 14 AMU, so that's 14. And we have 5 hydrogens, each hydrogen weighs 1 AMU, so that's 5. Because there's 1 hydrogen on each of these. So add all those up, and that will be 79. So in the mass spectrum for this, you look at the x-axis, which has the mass to charge ratio, M to Z ratio, which is really just the mass, because the charge is always positive 1. That's on the x-axis. The percent relative abundance is on the y-axis, and you would notice that at 79, you would have that molecular ion peak. So because those two molecules have a different molecular mass, you can distinguish between them using mass spectrometry because they have a different they'll have a different molecular ion peak. So you take the mass spectrum, look at what the mass of the molecular ion peak corresponds to, and see which molecule has that mass.